Hi there everybody, this is Austin Hoggett here to give you another lecture from the OpenStax Intermediate Algebra textbook. This time we're going to be talking about Chapter 7 on factoring. We've got 2 or 3 learning objectives to get through with this lecture. You can see here that we'll start with the conversation around the greatest common factor of 2 or more expressions, and we can have up to 3, possibly 4. It's really about as many as that you'll see. We'll also talk about finding the greatest common factor from a polynomial in general. So these will be applicable to lots of scenarios. The last sort of scenario is factoring by grouping, which is in a case where if I have multiple terms and I can't exactly find a common factor other than 1, let's say, then how do I approach those problems as well? This is the only section that we'll talk about for, let's say, a Math 095, but this particular topic comes up a great deal further along in developmental courses as well as your college algebra. Let's start on this first topic here. How do I find the greatest common factor of 2 or more expressions? Let's talk about what factors are. I want to draw your attention to the analogy here that when we talk about factors, we're talking about the product of 2 things that come together to make some new term. So in the instance on the left here, you see that as we find the product between 8 and 7, we get this numeric value 56. To ask what is the factored version of that product is to reverse the direction and figure out what are the 2 things that I multiplied together to get back that number in the first place. In the same way, we can think about the analogy for polynomial expressions. So in the right here, I have something like 2x times the binomial x plus 3. These are the factors of some larger expression. So when I multiply them together using either the distributive property or some sort of FOIL method, then you'll get this product, a larger polynomial, in this case 2x squared plus 6x. What we're talking about with factoring is how do I start with some composite expression and break it apart into the factors that it's constructed out of. So how we piece these things together will be the conversation that we have here. So there's a lot going on here. Let's kind of break it down. At the top here, we start with, as usual, a definition. What I mean by the greatest common factor of 2 or more expressions is simply whatever the largest expression is that I can sort of pull out of whatever is given to me. So let's start with the simplest example. Again, we'll use just some numeric values. Here I want to know what are the greatest common factors between 36 and 54. You'll notice on the right-hand side here that I've broken this down using a factor tree. In other words, we're looking for the prime factors that these numbers deal with. And that's a solid approach. You'll notice that really what's preferable is to not use the factor tree, but this sort of setup here where I take each of the terms and I find how they break down into their primes by listing out those factors. So 36, if I don't know the primes, I can just start by listing whatever 2 products make up 36 in the first place. We're interested in getting down to the prime values typically. So while 36 is really maybe something you've memorized as 6 times 6, 6 and the other 6 would both break down to 2 times 3 and 2 times 3. So you can see the product 2 times 2 times 3 times 3. Similarly for 54, I might not know that the prime factors are what they are, but I can start by just finding any 2 numbers that will multiply to give me that number. Now in this instance I use 9 and 6, where 9 breaks down to something like 3 times 3, and again we have 2 times 3 as a replacement for that other value. So the next step in this series is to identify what are the common factors. It's literally in the title. What is the greatest common factor? Well, I'm just looking for, in my lists, anything that shows up in both. So you'll notice what's highlighted in blue. I have at least 1 pair of 2's in common. I have a couple of pairs of 3 in common. And notice that each of those pairs are only listed once to create the GCF. So the product of those common factors tells me that the greatest common factor between 36 and 54 is 18. Now this is generally speaking not where we'll end this sort of quest, but this is at least the sort of beginnings of finding a way to factor certain expressions, polynomials or numeric values alike. So again, a quick rehashing. How do I find the greatest common factor of two expressions? Well, I want to start by looking at the coefficients. Factor those coefficients into their prime values. We'll also look at the variables if there are any involved and sort of use the expanded form to list out the sort of product. So for instance, something like x squared, I would write out as x times x to be explicit. Once we've listed all the factors, we're going to match them in that column formation that you saw a moment ago and identify what are the factors that are in common to both of my lists. Then we will together multiply all those common factors to get the GCF. So here's my first example. Here I'm asked to find the GCF between 48 and 80. So again, I'll start here by saying, okay, I've got my terms 48 and 80. So for instance here, I might know that to get to 48, I can multiply, let's say, 4 times 12. But neither of those are prime factors. And so I might choose to instead continue breaking these down further. So for instance, 4 we would say is the same as 2 times 2. And 12 we could break down into 4 times 3, which again we would say 4 is going to be another pair of 2's. So there's my list of prime factors for 48. Similarly for 80, I could start by just picking some arbitrary values that I have memorized. I know that 80 is going to be a product of 8 and 10. We could break these numbers down as well. 8, it turns out, is just 2 times 2 times 2. And 10, in this case, is going to be 5 times 2. So we'll replace this. Again, I have 1, 2, 3 2's, and then 10 we replace with 2 times 5 like this. The next step is, again, to find what is it that these things have in common and create this GCF. So in red here, I'll highlight the things that we have in common. I see that we have at least 1, 2, 3, 4 pairs of 2's all in common here. So I will create a product of those to get my answer here, which is that the GCF should be equal to 16. So as I mentioned, this is not really the endpoint for a lot of questions that involve finding the greatest common factor. It's in pursuit of some other venture. So let's take it a step further. Not only do I ask to find the greatest common factor between numeric values, but they might include some variable expressions as well. You see an example here. I'm asked to find the GCF for 27x to the third, 18x to the fourth. Let's look at how these numbers would break down as well. So 27x to the third. Looking at the coefficient 27, that is going to be the same as the product of 9 times 3, where again I can use the prime values 3 times 3 in place of 9. So my expanded form of the x term is also involved here. So I would say x to the third is just x times x times x, like this. And we can repeat this process for 18x to the fourth. 18 again could be something like 9 times 2, where we replace 9 with our pair of 3's. So there's the coefficient broken down to its primes. And again, I've got something like 4 x's needing to be multiplied for my expanded form of x to the fourth. Looking at these two lists, I can see that I have at least 2 pairs of 3's involved in each case, and at least 3 x's involved in both lists. So here I'm creating my GCF again by writing out each of the common factors that I see listed above. So together I get 3 times 3 is 9 for my coefficient. 3 x's gives me x to the third. So this is with 2 terms. What if I add a third? How does this go? In this example, I'm asked to find the GCF of 21x to the third, 9x squared, and 15x. Well, as you might assume, I'm still going to list out the products just like we did before. I want to start with 21x to the third. And in this case, looking at the coefficient 21, that breaks down quickly to 7 times 3. And of course my exponent here, x to the third, gives me x times x times x, like this. 9x squared would break down into 3 times 3 times x. And the last one here, 15x, we're going to have a product of 3 times 5, and then just single x, like this. So whereas before we had 2 terms, now we have 3, so we have to include that third item as well. So only terms that are involved with all 3 of these we would include as part of our GCF. So from the list here, I can see again that I have at least one 3 involved in all 3 of my lists, and of course one x involved in all 3 of my lists. So the product of which is just going to be 3x. So despite how many terms we might have, you can see this procedure is pretty much the same. And one thing I'll note here is that although we've been trying to break down our coefficients into their prime values and expanding each of the x terms, there's maybe a shorter heuristic way to think about this. We'll look at some examples in a moment, and I'll point that out. So as I mentioned too, the act of finding the greatest common factor is often in pursuit of some larger goal. This is that larger goal, factoring a polynomial. So let's look at, again, something that is required to do this operation. I have to understand, in essence, how we use the distributive property, not just in the forward direction, meaning how do I find the product of some monomial times binomial term, but also how to go from a factor of AB plus AC into the format that we originally think of for distribution. Identifying the fact that I have a common term, in this case A, is required to understand how we do the factoring. So instead of generalizing, let's look at a specific case. What we're going to find is the GCF of all the terms involved for our polynomial, and then we're going to try to rewrite each of these terms as the product of the GCF and whatever remaining factors are included. Then we'll point out this distributive property that's used in reverse, and if we're finished with the problem, we should be able to confirm that we're going to have the correct answer by multiplying out back all of our factors to show that it gives me back the original statement that I had. So here's our first case. It's very simple. And again, I'm just going to take each of these terms and use this column method that we showed at the beginning. By identifying the GCF between these two terms, I'll then rewrite the polynomial. So given the term 4x, again, if I want to break this down into its primes, it's something like 2 times x. 12 is simply going to be 4 times 3, so that's another 2 times 2 times 3. So very simply, our GCF here is just going to be these pairs of 2's involved. So my GCF is just 4. This is where we try something new. We've given the original polynomial 4x plus 12, but we'd like to rewrite this polynomial in terms of the GCF times the remaining factors. And the reason this setup for the columns is so helpful is because I can pick out very clearly what the remaining factors are. They're the ones that have not been highlighted. So if I want to rewrite 4x as the product of the GCF and the remaining factors, it's just going to be 4 times x. 12 is also going to be simple. We have 4, the GCF, times the remaining factor, 3. So notice in particular how this matches almost exactly to the sort of second half of our distributive property. I have in several occasions shown this. We have something like the factor a times b plus our factor a times c, the product of which we can use the reversal of that distributive property to pull out the common factor a. And what is left in the parentheses is the sum of our remaining factors. So using this same principle, given our polynomial, I can pull out the factor 4 and multiply it by the sum of the remaining factors, in this case x plus 3. And that's our solution. So here's the factored version of the original expression 4x plus 12. And again, we can kind of check ourselves by understanding how the distribution occurs. I should be able to multiply a times b plus c to get back the original expression. And given that this is such a simple case, it should be clear that that is our solution. Let's look at another example here. Here I'm asked to factor 5x cubed minus 25x squared. Let's again start with breaking down each of our terms. So 5x to the third, very simply, is just going to be 5. It's a prime number. And x cubed is just 3 x's multiplied together. I'm actually going to, in this case, ignore the fact that I have a negative 25x squared. Only when I rewrite this as the product of the GCF and the remaining factors will it really become relevant as to what the sign is. For now, I'm just interested in how the term 25x to the second breaks down. 25 in this case is actually a perfect square value. That would be 5 times 5. And of course, x squared tells me to multiply x together twice. So what's our GCF? Well, given the factors here, they both have a common factor of 5, and at least 2 x's involved as well. So that gives me a GCF of 5x to the second. So again, notice that the column setup here is really handy for rewriting the given expression as the product of the GCF and the remaining factors. So I'll start by rewriting the expression. I have 5x to the third minus 25x to the second. That first term, though, is going to be rewritten as 5x squared, our GCF, times the remaining factor, x. And again, if you look at our list, it's very clear that's the remaining factor. Similarly, when I use this GCF for the second term, I have this sort of negative sign just sort of stuck about. So negative 5x squared times the remaining factor of 5. So again, using the reversal of this distributive property, I can pull out the common factor 5x squared and multiply it by the sum of the remaining factors. If you look at the first term, I'll have x left if you pull out the 5x squared. If I look at the second term, I'll have minus 5 if I pull out the 5x squared. And this is my answer. 5x squared gets multiplied by the binomial x minus 5. And that's going to be the factored version of the original expression that we had. So in this instance, I mentioned that I would initially, at this column stage, ignore the fact that I have a negative sign. Sometimes it's actually imperative that we pull out a negative factor as our GCF, but we'll look at some examples in a minute to clarify when that's the case. So in this example, I have, again, a fairly simple expression, negative 4b squared plus 16b. And I can actually probably illustrate in this instance why it is that we can pull out a negative factor. But let's look again, just by ignoring the signs for a moment, what the GCF is between these two terms. 4b squared is going to break down here nicely to 2 times b times b. 16b would be, again, 4 times 4, which is going to give us 4 2's in total, times a single b term like this. So my GCF, between these two factors, between these two terms, I have at least 2 2's involved and 1 b, which gives me a GCF of 4b. Now in this instance, like I said, the negative sign is sort of irrelevant for this first process. I want to rewrite each of these terms, though, as the product of the GCF and the remaining factors. Since this first term is actually already negative, I'm going to include the negative sign out front, but not necessarily as part of my GCF. So negative 4b, the remaining factor is just b. Similarly, for 16b, if I pull out that GCF 4b, the remaining factor is a positive 4. Now in this instance, my final step is again to pull out that GCF from both of my terms and multiply it by the sum of the remaining factors. Since I left the negative sign out front at this stage, my first term here should actually be minus b. So it looks something like this. So here's my product of the GCF and the sum of the remaining factors. So let's look at the next sort of phase of this type of work. Not only can I have single monomial terms as my GCF, but I can also have binomials as my greatest common factor. In this particular question, you can see that really my two terms are broken down as about as much as I can have them broke down to be. Something like 5q times q plus 7. If I factor it, is really just going to be the product of all of those terms together. In this case, you'll notice too, again, I ignore the sort of negative sign on that second term, but I'll note that it doesn't really change much about how I'm going to solve the problem. Even this binomial being involved doesn't really change much about how we find the GCF in this case. But you'll note that the only common factor between these two terms is q plus 7. You might also think to actually do some distribution beforehand, but what you'll find is what you end up with is too many terms to really solve this problem. So we'll kind of see how this might look in a slightly different scenario, but the idea here is that you want to be able to understand that your GCF doesn't have to just be a single term, and that trips people up a lot of times looking at these types of problems. So my GCF of q plus 7 means that when I rewrite each of these terms as the product of the GCF and the sum of the remaining factors, it's going to look something like this. I'll rearrange the first term. I have GCF q plus 7 times the remaining factor 5q. And I'm again going to leave my negative sign as it was and find the product of my GCF times the remaining factor, in this case just 6. So when I pull that GCF out, I end up actually with a sort of different scenario than before. I have a binomial times another pair of terms. So a binomial times binomial. But that is in fact my answer in this case. What was important here is that the GCF, again, happened to be not a single term, but a binomial term. And that's exactly the kind of information we'll need to factor by grouping. So let's look at a couple more examples that illustrate instances where you'll have to factor by grouping. So a quick sort of step-by-step here is that we need to group terms with common factors. A big key sort of signifier that we need to factor by grouping is that I'll have 3 or 4 terms, none of which will have a greatest common factor other than 1. In other words, I can't factor something out from all of my terms simultaneously, but I can do it in groups. So we'll pair either the first 2 terms or the last 2 terms and identify a common factor in the way we've shown in the previous examples. And then what will evolve is this binomial that we saw like in the last example. It will crop up in what identifies as the GCF now is a binomial that we can pull from these terms, right? So let's look at a specific example instead of listening to me draw on about it. Here's my first example. I'm asked to factor the following: xy, a single term, plus 3y plus 2x plus 6. Again, if I were to list out these in a sort of factored version as we've seen before, and it's fairly simple in this case. For instance, xy only factors to give me x times y, 3y only factors to give me 3 times y, and the rest. What you'll notice is that to find the GCF is sort of impossible. There's really nothing that these 4 terms have in common other than, let's say, 1. So I could claim that they have a GCF of 1 and rewrite each of these terms as the product of 1 and the remaining factors, but it essentially would look exactly like how we started. So this is not really a useful approach. Instead, what we'll do is start by looking at the first 2 terms alone. In other words, I'm going to group these 2 terms together and ask the question that we would have previously, which is, what would be the GCF of just these 2 given values? You'll note that I can sort of split my columns up this way and pose that question. So the first 2 terms here look to have a GCF of just y. And if I pull that common factor out, and the sum of the remaining factors would be x plus 3. Now this is the binomial that I was talking about that should show up. And if we look at our second pair of terms, I have 2x plus 6, and by grouping them with parentheses, I can ask the same question as we did before. What would be the GCF between 2x plus 6? Again, looking at my list here, it seems that 2 is the correct answer. So if I can pull out a positive 2 here, the sum of the remaining factors here would be just x plus 3, exactly as I expected. Now this looks like the scenario we had previously, where a binomial is now our GCF. By identifying that binomial as our GCF, I can pull it out front and again rewrite the sum of the remaining factors. In this case, y plus 2. So there's my answer. When factoring by grouping, again, this idea that the binomial shows up in both cases is important. If it does not show up in both cases, one of two things has happened. I've either misidentified the appropriate combination from the original problem, and I need to sort of consider maybe reorienting the terms here. For this case, since it's addition, I really could add these four things together in any order that I want. So I have to consider that I might have chosen the wrong pairs or the wrong groups. Another example of having screwed this up slightly is if you misidentify the GCF of one of your pairs to have been a positive as opposed to a negative GCF. Let's look at one more example. In this instance, I start with the question of factoring x squared plus 3x minus 2x minus 6. Now, I'm not going to try and illustrate in this case that these don't all have a common factor. I think that should be clear at this point. But instead, let's focus on the first two terms here, x squared plus 3x. Identifying the GCF in this case, I would say that they both have at least one x involved. So if I factor that one x out of each of these terms, what goes in the remaining as the sum of the remaining factors is going to be x plus 3. Actually, the same binomial as the last example. The second two terms here, though, are negative 2x and minus 6. We might, instead of identifying the appropriate factor as a negative value, claim that the appropriate factor should be a positive 2, let's say. So let's go on the assumption that positive 2 is our GCF of these factors. What you'll note is that my binomial in the parentheses here would be negative x and minus 3, which is sort of clearly not the same but close to the same as the binomial that I think that I should end up with. Again, this is a big signifier that I've picked out the wrong GCF. And in fact, if I were to instead have chosen not the positive 2 GCF, but the negative 2 GCF, the remaining factors would have to have then be positive x and positive 3, just as we would expect. So to kind of check myself, again, I can use the distribution to make sure I get back the original pair that I was expecting. So negative 2 times x is negative 2x. Negative 2 times positive 3 gets me to negative 6. So I, again, have identified the correct binomial that shows up in both cases, and I can pull that new GCF, the binomial x plus 3, out, multiply by the sum of the remaining factors, x minus 2, like this. And there's my solution. So there you have it. Those are the 3 learning objectives for this section on factoring. Best of luck learning this material. I'll see you next time.